Yeah.
Hi, my name is Nico and I'm part of AVL SET's electronic design team.
Hi, my name is Chung and I'm from the Model and Control Design team.
Okay, in this case I would like to start with my introduction to our presentation on holistic and comprehensive development methodology for inverter drive systems. And I would like to start with a definition sort of introduction. So first of all, I would like to define what we understand as a hill. Generally speaking, we can abstract an inverter as some sort of DC link device, some sort of power stage, and in between there's a control unit. Let's call it control unit. And everything is connected through various interfaces. And what we do with it is we have DC coming in on the one side and AC leaving the inverter on the other side. So, and frankly speaking, I would say we generalize or we define the hill as a test bed where absolutely everything except the control unit is virtualized. So in this case we have a virtual DC link unit, we have a virtual power stage, but we have the real control unit and we would like to have the real software tested on that. In contrast to that, we have the power hill, where we can say that actually the entire inverter is made up of real components. So there we really have the real inverter with every single interface in it. And what we do is we want to test it on rated condition, we want to calibrate sensors, and we want to see the overall performance of the system. So with that speaking, I would like to, or with that knowledge, I would like to start to point out our possible development process for inverter testing. So let's picture an inverter development process where we in theory can divide or split the development process between the people that design the control hardware and the control units and the control software, and the people that design the power electronics around it and the mechanics and all the mechanics. So cooling systems, housings, EMI concepts and all that stuff. And at some point we merge those two components and we create an inverter from that. In order to be sure that after this merging process the whole thing actually works, we would like to test every one of our independent steps that are indicated here in the presentation. And what we want to do is we want to fail fast. So we want to make sure that we find errors while we make them and not just after merging it, because then errors are costly and we need to revert the whole process. So what we need is an adequate testing tool chain to provide or to cover for these needs. So what we suggest is a combination of a hill testbed and a power hill testbed, where we on the hill testbed more or less test on low and harmless voltage levels, and we have a very low cost testbed that doesn't require a lot of time to set up, and it's very good to just try out some things, because if we mess up, well, there's not much going on there, so we won't break anything. But at the same time, we need, in a later stage, we need the power hill testbed, because real calibration of sensors can only be done there, and we can only test our real performance there. But to make optimal use of these two test beds, we have to look into the requirements of these. The standard tool chain when it comes to hill testing starts with modeling electric machines and power electronics. Then we sort of need some way to test these models, which is not really defined how we do that. And then we can start focusing on our product design, which we discussed earlier. And after that, we can finally proceed to hill testing. And when we have find errors there, well, the natural thing would be step back and check our models. what we have then. After this cumbersome process, after these cumbersome iterations, on some point you would then merge those two components, so signal level and power electronics, and then you would proceed into sort of road testing or on some dynamometer or whatever, because this is what you do. With our proposed tool chain, you start directly with product design because the modeling is already done by us. Then we proceed on some sort of digital testbed, which we call the inverter hill, where you can test your product already in very early development stages with the exact same models as you will have on Power Hill. So what you learn there is not only how your inverter signal, how the signal part of your inverter will behave on Power Hill. You can also start by some sort of rudimentary calibration of your controller parameters. Then you proceed on Power Hill, you calibrate your sensors, you test the performance of your inverter, and you can proceed to road testing directly.
So, let me quickly introduce to you the hardware setup that we used for our proof of concept. The central part here is the unit under test, which is a control unit for a state-of-the-art inverter. And we have here what we call our fast signal interface. We have here basically through this interface here, we read in the PWM signals, which we can do up to 1 megahertz switching frequency. And we have also at the same time here the interface for the current sensor emulation, where we feed the signals, the emulated signals from the current sensor back to the unit under test. What you can see here is a failure injection matrix, which we have in between our FPGA-based emulation system and the unit under test, so that we can freely introduce shorts or opens in each of the signal paths here. We focused mainly in this setup on decentralization. So what we have here is basically that the computing units are spread over the hill testbed. Because in here we not only have the interface, we also house the inverter model. So all the phase currents are actually calculated in here, as well as the rotor sensor emulation, which is based in here. Then the last part of the proof of concept setup is here our control unit for the hill environment, which is the same control unit which we use in our Power Hill systems, and where we house or where we run our motor models and machine models. Also, this is the interface to the host PC and to what you will see later. The benefit of this is that actually all the fast interface or the fast data transfer we can do here through optical fiber, and only a very short distance is covered with copper wires. So we're absolutely immune to EMI interference, and we significantly increase the signal integrity of the whole system. The decentralization here is just one setup here, but we could also, because we're absolutely independent in this distance, we could place this into a different room or into a completely different location, having no trouble at all with signal integrity and signal runtimes. Thank you.
This is a screenshot of the user interface on our host PC. On the right-hand side of the screen, you can see the user interface of the hill system, where all parameters of the motor, inverters, as well as the scaling gains and other required parameters can be set. In the user interface of the hill system, we not only set the hill parameters, but also observe hill internal values. different test scenarios such as change of rotor speed, simulation of wrong measurements, and many other test features can be emulated. The user interface of the unit under test, the inverter, is placed on the left-hand side and at the bottom of the screen. Here, we can parameterize the inverter, give the set points for the inverters, and observe the inverter measurements. On these left windows, we can see the phase current measurements of the inverter, as well as their equivalent values in DQ coordinates. Our inverter can be operated in torque and current control modes. Firstly, we would like to show the inverter operation in current control mode. The inverter is set to current control mode respectively. The initial rotor speed is set to 5 RPM. The initial current set points are 0. Then the UT is enabled. The actual D and Q currents vary around their 0 set points. Then the set point of the Q current is set to 100 ampere. It can be seen that the actual Q current goes to 100 ampere while the D current remains to be 0. Now, the rotor speed is ramped up to 200 RPM. Then it is increased up to 1000 RPM. The Q current set point is changed from 100 ampere to minus 100 ampere and back again to 100 ampere. It can be seen that current follows the set point and the system remains stable. Now the rotor speed is reduced to 0 and the current set point is reduced to 0. Then the UT is disabled to finish the test. For the second test of the low voltage hill, we would like to show the torque control mode of the inverter. So the inverter is set to torque control mode accordingly. The initial rotor speed is set to 3 RPM and the initial torque set point is set to 50 Newton meter. After enabling the EUT, the actual electrical torque reaches its set point of 50 Newton meter. Then the rotor speed is increased to 1000 RPM. The torque set point is set to 100 Newton meter and the actual electrical torque follows its set point immediately. In order to show the four-quadrant operation of the torque controller, the torque set point is changed from 100 Newton meter to minus 100 Newton meter, and the rotor speed is changed from 1000 RPM to minus 1000 RPM and back again to 1000 RPM. It can be seen that the inverter controller operates as expected in the low voltage hill system. Now it is interesting to know whether it does the same thing in the power hill system. So here is a screenshot of the test with the power hill system. For better understanding, we arrange the user interfaces similarly to the test case with the low voltage hill system. With the power hill system, we perform the same two tests that we carry out previously with the low voltage hill system. Firstly, we would like to perform the current control mode of the inverter. The initial rotor speed is set to 200 RPM. The inverter now is enabled. Then the Q current set point is increased from 0 to 100 ampere. Afterwards, the rotor speed is increased to 1000 RPM. The Q current set point is set to minus 100 ampere and it can be seen that the actual Q current reaches the new set point. Then the Q current set point is changed by to 100 ampere, so does the actual Q current. Now we would like to perform the torque controller test with the power healing system. The initial rotor speed is set to 200 rpm and the initial torque set point is 0. Then the UT is enabled. The torque set point is set to 100 Newton meter. It can be seen that in the plot that the actual torque follows the set point immediately. Then the rotor speed is increased to 1000 rpm. The actual torque remains at 100 Newton meter despite the rotor speed change. In order to demonstrate the fork Van Run operation of the torque controller, the torque set point is changed between 100 Newton meter and minus 100 Newton meter, and the rotor speed is adjusted between 1000 rpm and minus 1000 rpm. So with these two tests, it can be concluded that the inverter control unit together with the power electronics and drivers also operated as expected in the power healing system. In order to show that the results of the low voltage hill can be compared with the results of the power hill, we perform the same current step change test in both systems. The drive system is operated in a stable operating point with D and Q current set point are 100 and 0 amperes respectively. Then a step change of the Q current set point from 0 to 200 amperes is applied. This step change of the Q current set point is performed twice with different controller parameters. The test is then repeated in the power healing system. So here are the plots of the resulting currents in dq coordinates. The resulting currents with the low voltage healing system are presented on the left hand side, while the result of the power healing system are on the right hand side screen. Here are the results with the first controller parameter set, and here are the results with the second controller parameter set. It can be seen that current transients are similar in both low voltage and power healing systems. This comparison shows that, from one hand, the result of the low voltage hill and the power healing systems are comparable, and the current controller can be verified with the low voltage healing system. Moreover, it is possible to optimize the controller parameters with the low voltage healing system. From the other hand, we can see a small difference in the result of the two systems. The D current in the low voltage system remains stable around its 100 ampere set point, whereas there is a small offset between the set point and the actual value of the D current in the power healing system. This current offset shows us that although being a powerful tool to design and optimize the inverter controller, which accelerates the inverter development process, there are still effects which are not emulated by the low voltage healing system. Therefore, the power healing presents an essential tool for the inverter testing. With this comparison, we are now at the end of the presentation. Thank you for watching.